So welcome everybody. My name's Josh Kuckens. I'm a photographer based up in Northeast Kingdom. And I met Jim here while working for a dog walking company. He had two dearly departed now English bulldogs, Daisy and Mosby. And so we got to know each other pretty well through some dog activity. And we kept in touch, especially about astronomical events. I just wanted to play a few videos here to start off, and then I'm going to offer some remarks after that.
All the videos and pictures taken by Josh were in the state of Vermont. Watch closely for the satellite.
This was last October.
Those coyotes?
Yes. Yeah. They joined me for many of the viewings.
Yeah. They are excited.
Is this the one with the native?
That's later.
Is that an original soundtrack? Or
It's a pack of coyotes. Oops, bear with me here.
Your desktop looks like my desktop.
Yeah, nice and organized, right?
Oh, that's a lot of photos.
Big Dipper.
I'm just going to leave still up here so that you can actually see me up here. So just to continue on Jim and me and Jim's background. So we kept in touch, especially about the eclipse that happened last year. And that event in itself was incredible. Little did I know that was not even necessarily the biggest solar event of the year. So about a month later, oh, that's too bad. About a month later, Jim sent me a message sort of warning me that there was a very large solar storm coming. And I photographed the night sky quite a bit, mostly the Milky Way and, some deep space targets here and there. But I didn't really have too much of a grasp of the aurora. I kind of thought it was just an Arctic thing. Heard that sometimes there were some faint viewings kind of on Canadian border states. And obviously I was very wrong because we had quite a few storms last year. So that first night, I set out to a dirt road near our house that has sort of a northerly view. And before I even stopped to park, I could see a glow in the sky. And so I got out, set up my tripod. I took just one sort of test exposure, maybe 10, 15 seconds, just see what I could see. And when that image review came on the back of the camera, I just, just absolutely bursting with greens and purples and reds. And I just, in the literal millions of times that I've looked at the back of my camera after taking a picture, I just have never felt anything like that. I think astrophotography is at its strongest when it conveys this almost indescribable sense of scale and just of systems and cycles that are far beyond the human lifetime, and just really kind of put things into perspective. Just these cycles that have been happening for billions, millions of years, and they will continue long after we're gone. I just feel like with the Aurora, that is the best way I have been able to capture that feeling. Some of these displays, like the first one that I showed, I'm not an overly emotional guy, but I fell to my knees when I saw that. It's just, there's just nothing like it. And it really makes you understand how humans for a long time worshipped the sky and based religions off of astronomical events. So without further ado, I'll kick it to Jim, and
Maybe you can help me.
yeah, we'll transition our presentation here.
Thank God Josh was here. I wouldn't have been able to do this myself. This is a brand new Mac, and can you hear me, John? Excuse me, I'm going to stumble over here. Excuse me.
Get through?
Stability isn't what it used to be. Thank you.
Yeah.
Okay. See if this thing works. See, the thing is called a laser. It's a quantum device. Yes. I'll make other references to that as we go on. In fact, one in a second. So acknowledgements here. In tackling this endeavor, both Josh and I relied heavily on NASA and NOAA Space Weather Prediction Center. I'll say a little bit more about that later, but there is public domain stuff from which we grab data and images that you all can do yourself as easily as looking at the weather forecast on your phone or computer. This is unbelievable. And if the government shut down, they couldn't shut this down for reasons I'll talk about. Of course, Mad Rear R should have been number one. Anyway, the challenge that Sam and her colleagues took to put this on, Julie, and the little bit I had to do with it was I got them linked into the International Quantum Year. So this is part of a worldwide effort in 2025, which is the 100th anniversary of Schrodinger's equation, okay? So quantum mechanics is essentially 100 years old, and the worldwide science community has been celebrating it in countries all over the world, including Ukraine. I have colleagues at Dartmouth College, one of whose specialty is on electromagnetic phenomena in the upper atmosphere. So thanks to Jim LaBelle for his advice. And I would like to thank our families, because they were always wondering, what the hell is Josh and Jim doing at 2 a.m.? And then Ray and Julie, Parker and Sam, and for setting up the quantum stage 2 weeks ago. It was a fabulous event. And Josh, can you? And John, yeah. Josh, can you?
Ready to click.
Yeah, ready to click. Uh-oh. Oh, I've got it. Do I have the mouse?
Oh, I've got it.
Okay.
Here we go. Here we go.
Oh, okay. That is, after I got out of the Army, I worked at NASA for 2 years. I was a orbital and attitude technician for these scientific satellites that were in highly elliptical orbits. They would fly within 90 miles of Earth and then fly out 1,000 miles apogee every 88 minutes. And we had to keep these satellites oriented with its axis of spin in the perpendicular to the orbital plane. And all the solar activity, daily solar activity, would have some effects on how this satellite was positioned in its orbit. And when there was a big activity, this satellite would feel it heavily. And we had to do drastic actions to put it back in its correct state. Okay, thank you, Josh. So, as Josh said, this is art on an immense scale, an immense canvas, this Aurora. If you go to that NASA website, it'll predict what the Aurora is going to look like. And this was back in, I don't know, September, I forget. There it is, September 1st. Yep. And that red line shows that Vermont was definitely going to see the Aurora, and I got pictures on my little phone with that. But this shows, you can get this by your lonesomes, right? If you go to the NASA website. And actually it's animated. And this is one of Josh's still pictures. What is the name of the mountain with the windmills on it?
So, yeah, is it just Lowell Mountain?
Yeah. Yeah, I think Albany's on the other side, right? Albany's on the other side. Okay, next slide. Or whatever it's going to be. So I went over this with my spouse, Mary, yesterday, and she said, when I finished the talk, she said, you said some words that you really need to say at the start. So the bottom line here is that the Earth's beautiful aurora is created by quantum reaction of simple atoms in our atmosphere relative to the magnetic field is generated by the sun 93 million miles away. We're talking about effects down at a billionth of an inch, giving off light on atomic oxygen due to generation of these immense fields and the flux of particles 93 million miles away. Next slide, please. This is Josh's Milky Way picture.
Wow, that's
Okay, we're actually looking into the center of the galaxy. The black hole's out there somewhere in Aquila or something like that. So our solar system is like 80% of the way out on the fringe of the galaxy. Next slide. So orbit's going to be a concept that we deal with at the atomic level, but need to point out the orbits of the planets, right? And, oh, look, a comet. Asteroids. Click it, Josh. Planet, let's see, so scale here is millions to about 1 billion miles out to Neptune. Poor old Pluto's not a planet anymore. The planet's orbit with periods of about a quarter of a year, that would be Mercury, to 164 years, which is Neptune. Next, click. So the Earth has a 1-year period. Click, click, click. Yeah, there, that's Earth. And then Mars has a 1.9 year period. Next slide. And gravity, key here is gravity is the binding force. It's a weak force, but it's big on a scale of millions and billions of miles. It's weak, but big on a large distance scale. So, what life support does Earth have which Mars does not? This is a question for you all. Here's Earth, atmosphere is one. What's this, Mars? What else is Mars? Water, well, it used to have water, yeah. Okay, next slide. Okay, we got the atmosphere. Magnetic field. Okay. I'm going to go into a fair amount of detail here, but clearly, we know we all have used compasses and so on. So it turns out that the North Pole is actually the South Pole of a standard magnet. but at any rate, it has these lines like an apple core, right? You cut an apple, and the intensity increases at the poles. And that's why the aurora tends to be isolated where the lines of intensity are squeezed together. That's a picture of a bar magnet. Okay, to understand the solar wind, we need to understand what a magnetic field is. Mary didn't believe me, but she sort of got it toward the end, so I kind of feel like I'm going to do it anyway. Okay, next slide. So there's the bar magnet, and these are spins in, say, iron. All the iron atoms are very sensitive to magnetic fields, and if you get them lined up in one direction, they will stay that way. They get frozen in. That's why a bar magnet retains its magnetic field. Next slide. Oh, it shows what happens to your compass as you go from one side to the other. Next click. Oh, okay, the aligned spins of atoms, all right, makes a permanent magnet. The motion of charges, for example, electrons, as in an electrical current, make the same field. Okay, I have a demo we can run after the talk.
Like identical or similar?
Pretty close, pretty close. Not the same intensity by any means. So this, in fact, the intensity of this magnet is probably more than the Earth magnet. Okay, I'll say a little bit more about that later. But at any rate, you take a standard battery, 1.5 volt, hook a wire up, wrap a copper wire around a nail or any convenient cylinder, let it run, put your compass near it, or if it's the nail, as the case of my demonstration, you can pick up metal objects with it. Okay? So the important point there is, don't change the slide. No, it's okay. The important point is when you have electrons moving in a circular fashion, they generate a magnetic field. Even electrons moving in a straight fashion generate a field, but it's very special when they're wrapped in a coil. You get this standard north-south kind of.
Is the field toroidal?
Let's see. It's in all.
Like is
if
that
you,
three-dimensional?
yes, it's three-dimensional. Yes, it's three-dimensional. Yes, yes. Right. We're just taking a cut, one cut. It's just like the Earth's magnetic field is toroidal. Yes, very good. Next slide. So both the sun and the Earth have significant magnetic fields. Next click. Both rotate physically, right, in stability, in space. That satellite I showed was rotating, okay? It actually had a momentum wheel in it, so you could despin it and run your experiments, and then it normally would rotate in total so that it was stable, pointing in a stable direction. So it's like a top, right? Both Earth and the sun do rotate, and both have magnetic fields due to their rotation, okay? So the Earth's field is generated by its molten iron core. I've got a picture of this. The top of that core is about 2,500 miles, and another 500 miles on top of that is molten, and the inside core is solid. That's what Mars has now, a solid core. Right. Very good. I probably have a prize. That's great. That's great. So the iron core is there in Mars, but it's solid and it's not magnetized. They're actually remnant field. Can we go back, Josh? Okay. Sorry. Okay, so the iron is ionized because it's molten. And as we'll see in a second, because the Earth is rotating, the core is actually rotating slightly different rotation rate. It generates that magnetic field. Okay, just like the little coil, right? It's electrical currents moving in a cylindrical fashion. Okay, next slide. Here it is. It's a little more complicated than just one coil. The several. It turned out this is more recent stuff. They seem to be several cylinders that are rotating, kind of like convection currents, or what's the word? But at any rate, it adds up to give you the field that we know and love on Earth.
How did they discover there were 3 coils?
That's a good question. I didn't know this myself till about 3 weeks ago. But I saw some reference to it and a link to Nature magazine I get. So this is recent discovery, more or less.
Wow.
Okay, next slide. That was a great question. Sun's magnetic field. Next click. The sun's field is somewhat chaotic, okay? The poles of the sun rotate more slowly than the equator. We've got pictures coming up that shows the sun's rotation. And as we'll see, the sun has big holes, particularly when it's active, it gets these big black holes in it They're not just sunspots, they're like somebody's dug a trench, right? A massive trench. Okay, and those are local poles, and they do things that we're going to talk about. Next slide. Here's the sun. It's blanked out, but you can see those coronal loops, right? That's very high magnetic fields, all right? And the sun is boiling off ionized hydrogen atoms, as it turns out, protons and electrons, and they're, as we'll see, these loops push them toward Earth. So if Earth's over here, a big loop would push those particles in the magnetic field toward Earth. So next slide. These are called coronal loops, these things, and that's local high intensity magnetic field as opposed to the more general field. Next click. Okay, those are high magnetic field. Next. Protons and electrons boiling off the sun's surface or get caught in those magnetic fields, frozen in, and are propagated in all dimensions. But if the Earth's over here, they're going to hit us. Okay, next slide. Okay, that injection of these particles by the magnetic field is called the solar wind. Okay, next slide. Oh, it says magnetic field, protons. I got electrons. There it comes. I think it says something else. That's it. So they're all getting pushed to the right if the Earth was over there. I got a red button too. Yeah, there's the Earth. Okay, this is Josh's picture of the eclipse. I didn't want to doctor it or home in on it, but Josh, I've got this pointer. That's one of the coronal loops, right? And that's one of the coronal loops. Okay. Now, on a visible scale, it doesn't look very big, but on that other scale, those coronal loops are 1 million miles, all right? 500,000, 1 million miles. I mean, the sun is 1 million miles in diameter, roughly. Those coronal loops are half the size of the sun, and they're flushing stuff out into space all the time. And Josh said that is a fabulous picture. I mean, there it is. I remember we took a picture, and we saw that one kind of as a blur, but his photography is far superior to anything that I can do. Next slide. There they are. Okay, so this is one of the NASA satellites called GOES. I'm not going to go into the orbital details, it's too technical. But at any rate, this is a coronal hole, all right? And if you click it, Josh, the sun's going to rotate. You see it rotating a little bit? So this is taken over like 15 minutes. That's a big object rotating, right? They update this all the time. But that hole is massive. This is 1 million miles. What's that, 500,000 miles? It's only because of the activity we're having now on the sun. Normally, it would just be sunspots, right? This is not visible light. This is 193 nanometer radiation. They take about 10 different wavelengths, and I'll describe what wavelengths are later. But somebody asked me about IBM. When we print shapes for the smallest devices we can make, it's with 193 nanometer radiation. Okay, that is like 1/100th of a centimeter. They're very, very small. Okay, next. So the coronal hole is very strong. Oh, okay. At any rate, I've said the words. So the solar wind, as we'll see, washes over the Earth. So the sun's over here, solar wind's pushing this way. Here's the Earth with this magnetic field, right? The apple core. This is the sunlit side, right? So the solar wind hits the Earth's magnetic field, it pushes back on it. And actually, it's like you saw in Josh's Aurora picture, you could see some of the aurora kind of bouncing around. That's because of the interaction we're seeing up 100 miles in the atmosphere. And in fact, when we see our aurora, we're on the nighttime side, right? So all this is called reconnection. I don't even understand it completely, but this is the activity we're interested in for the aurora that we see, okay? So most of the solar wind is being deflected away from Earth. That's a good thing. I forgot to mention it. If Musk wants to go to Mars, no magnetic field, He'll die within 6 months because he will get the equivalent of 1,000 high-intensity chest x-rays. And they worry about that with even the space station astronauts. They're getting exposures far beyond a lifetime's worth, or close to it. Okay, next slide. So key processes we're going to be focusing on are fusion, solar fusion, and atomic excitations. I'm going to not spend much time on this other than to say the words. I had a nice picture of it. It's too confusing. I don't want to spend the time on it. You all know what solar fusion is. Or I'll say it again, but you kablooey, right? That's what it is. And atomic excitations, so big scale and small scales. Okay. So solar quantum nuclear fusion is the hydrogen it's due to the giant pressure on the sun and the core. Hydrogen is pushed together, and it turns out it takes 4 hydrogen atoms to convert to a helium atom, and the helium atom has less mass in total than the 4 protons. That difference in mass is mc squared. That's an explosion. And that 1 gram of hydrogen, if you compressed it, would power Burlington for a month. 1 gram of hydrogen. Okay, so it generates visible light, heat, ultraviolet light. Sun surface, again, repeating myself, protons and electrons are embedded in this rotating. As we'll see, that solar magnetic field rotates. I didn't say that, but we'll see it visibly with the NASA data. This is also called a plasma. That plasma travels to Earth 93 million miles in about a day, maybe a day and a half, okay? It's going maybe 0.1% of the speed of light. How long does it take light to get to Earth?
8 minutes.
8 minutes, right answer. So you can work out the ratio. It's like 0.1% of the speed of light. Speed of light is 186,000 miles per second. Next slide. Unlike planets, atoms have quantum electron orbits. Next slide. Click. The binding force is electricity, not in, on a scale of a billionth of an inch, less than a billionth of an inch. Okay, really small. The proton binds electrons, protons plus, binds electrons that are negative in what we'll see are called quantum orbitals. Next slide. Okay, I guess I moved things around a little bit. Quantum excitations of oxygen and nitrogen, mostly. There are others, but these 2 elements on kind of the right side of the periodic table are created by the solar wind. Okay, excitations, and this is happening in the atmosphere, as we'll see. Plasma collides with the Earth's atmosphere, typically from 90 to 150 miles up, as we'll see. That satellite got to within 90 miles of Earth. It was sampling the whole 9 yards, okay? Visible light, which we see, are quantized into colors. Those are colors we see in the aurora. Red and green prominently, some blue. We've got one of Josh's pictures on that, and violet. Next slide. So the quantum orbitals that are discrete, unlike the planets, you could have planets in between Mars and Earth, and you could, ratchet up the energy, and for every energy, you could have a planet orbiting the sun. That's not the case in an atom. They can only orbit certain energies. The orbits of the electrons only can have certain energies in order to stay bound to the atom. So here come some pictures. By the way, Ray mentioned this, uncertainty. It's not possible to measure electron position at the quantum level, right? Nor its speed. That's why 1 plus charged proton, 1 electron is about 0.8 of an angstrom, 10 billionths of a centimeter, 10 billionths of a centimeter away. It's circulating on a sphere. Next click. It's a spherical shell. So imagine the electron at any time can be anywhere in 3 dimensions on this spherical shell. Okay? It can be there with a particular energy, but its position and speed are not, you could measure its position, you would never know its speed. You could potentially measure its position, but you can never know its, what do I say, speed. I'm losing track of myself. Okay, we're interested in, I'm going to use oxygen as a paradigm for this. It's oxygen and nitrogen, which are mostly giving rise to the aurora we see on Earth. So oxygen has, can you click once? Should say 8 protons, 8 electrons, and there are also 8 neutrons. So the blue are neutrons, which are basically neutral protons. I won't go into that. But there are 8 protons, so there's 8 charges here. So you've got to have 8 electrons to make this a neutral atom. They're in this case, 3 shells. There's a spherical shell, like in hydrogen. There's a second spherical shell farther out, as in hydrogen. But there's a dog bone, okay? And there are other even more incredible shapes, like flying saucer shapes, okay, for the outer orbitals. But these are the ones we're most interested in. Again, you see 4 atoms here. The 4 atoms are moving in these orbitals. In fact, it's a 3-dimensional orbital. There are, you can only, I'm not going to get too wild. But at any rate, each of these atoms we're seeing here is in a dog bone orbital with the same energy, okay? One of them would actually be out in this space and one would be this way, but that's too complicated. So there are 4 of them, right? Moving in a dog bone. Next click. Multiple energy levels, including the figure 8, okay? And yet there are more. Okay, next slide. That's called 2s because it's the second spherical shell. That's 2p. P, I don't know why. It's probably French for momentum. I don't know. Okay, next slide. 1s. So the inside shell is actually labeled, this hydrogen atom would be a 1s shell. Okay, next slide. Okay, this is the meat of the talk, okay? This is the meat of the talk. This is a really, really quantum piece of the talk. I will say it took me 2 weeks to make this slide, okay? I wanted to do it, get the idea across. So I did my best, folks. Okay, so first excited state. What happened here? One click only, one click. Excitation of oxygen by collisions with the solar wind, okay? Okay, click. Orbital electrons are elevated to higher energy states. So this atom, with collisions with the solar wind, there are particles, there are protons, there are electrons, and there are actually cosmic rays coming from the outer solar system, some of which get through, but most of the collisions are with electrons or protons. Okay, click. It's pushed that p electron to the s state. Okay, so now that's the first excited state. Okay, keep that in your heads. Here's the second excited state. Okay, there's an extra electron here and there's one missing here. So click, bada bing, the collisions move that electron here into the 3s2 state. So there's now 2 electrons in this spherical orbital. Okay? This is the source of the aurora that Josh showed, that we see mostly, the reds and the greens. Okay? Created by collisions from particles in the solar wind. It hits the oxygen. I should say that where this is happening, 90 to 150 miles up, the oxygen is oxygen, atomic oxygen only. The air we breathe is molecular oxygen. It's 2 oxygen atoms that are bound together with covalent bonds. Okay, so they're hard to dissociate until you get higher up in the atmosphere, and they will be dissociated by collisions with these cosmic particles. So at any rate, high up in the sky, 100 miles up, it's all atomic oxygen basically. Lower down on the surface, it's oxygen molecule, 2 oxygens bound together. Okay, next click. So don't click yet. So the electrons, those 2 states that we looked at are unstable. They're higher energy Okay, we got them up there, but they're a little dizzy, right? They can't stay up there because they would like to get back to the original stable state, okay? So next click. So the order of magnitudes here, 1 to 140 seconds, right, in these excited states. I forget which is which, but okay, so this electron moves back down to the p orbital, right? Okay, keep that in mind. There's a change in energy here. It's a quantum energy coming up. Next slide, next click. Okay, click, 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 click. You tell me what it is.
It's the Aurora.
It's a quantum red light, right? These are waves. Ray talked about wave functions, right? So you can imagine waves of red light moving due to the motion or the relaxation of that electron back to where it wants to be. Okay? So drop a pond, stone in the pond, right? There are waves, and that's like generating light, so to speak. Okay?
Why does it generate as red?
Because of the difference in energy. It's a great question. I'll explain it in a second, but it has to do with the wavelength. Okay. In fact, it may be coming up. Click, Josh. Should be coming up over here. Okay, so this excited state wants to relax, right? From that 3s2 orbital. Okay, click again. Boom, 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 boom. Waves of green light, 550 nanometer wavelength. This is 630 nanometer, and I'll repeat that later. Okay, that's it. That's the quantum effect that's excited by the solar wind 93 million miles away when it impacts the Earth. So a little bit more detail here. Light spectrum in nanometers. Nanometer is 1/1000th of a meter. It's about maybe 5 billion, half a billionth of an inch. So light is pure radiative energy. We'll call that ERAD. It's a wave. It's a wave which was discovered by Maxwell in the late 1800s, but it's also a particle discovered by Planck around 1900. And the energy of that light is proportional to 1 over the wavelength. So the smaller the wavelength, the more energy. The higher the wavelength, the less the energy. The red has a longer wavelength. It's red. It was 630. The green has a shorter wavelength, 557, right? That's the wavelength of green light. Okay, next click. So here's the spectrum, what we get from the sun. All right, over here is blue, ultraviolet. Over here is over red and getting into the infrared. The green was 557 right about here. And the red was 630 right about there. Okay? The visible light peaks in the green and dies off to the left in UV and light. I remember giving a talk like this to children. What if our sun was blue? Everything on Earth, the plants are green. Would there be blue plants? I don't know. That's for the biologists. Okay, next slide. So quantum transitions in atomic oxygen emit the auroral light. Click. When the first excited state decays to the ground state, it's the red aurora. Second one gives us the green aurora. Red is 630 wavelength, and green is 557. Blue and ultraviolet would be down here around 450 or so, and I forgot what it would be. Infrared would be up around 800. Okay, there's the waves. The wavelength of the red is this, right? It's traveling this way. The green is traveling this way. The distance between the peaks is the wavelength, and obviously the green is shorter than the red. Higher energy, lower energy. Next slide. Josh's picture. This is just unbelievable. Because I believe, is there features in here, Josh, that other than red and green? That's why I chose it, but this one didn't have the comet in it. I don't know. At any rate, This is where in Hardwick?
That, I believe, is at the bottom of Center Road in Hardwick.
Okay, okay.
Looking north.
All right, so notice green is lower and red is higher. Red is higher up, but it's lower energy.
How expansive was that image? Is it a mile to the left and right?
I'm sorry.
That's a good question. I guess, yeah, probably about that.
And then it just dies off?
What's that?
And then it just dies off?
Yeah, it's really sort of northwest to the north,
Yeah.
and then kind of dies off in the other directions, unless it's a huge storm, in which case it's just
Sometimes it's overhead, yeah.
yeah.
So I would say, when I spoke at the start of the talk about this is art, it's art on a big canvas, and I kind of think that when a big storm, you're probably getting 100 miles, 150 miles horizontally. And you're getting here with the red up at around 150. So it's 100, this is 300 miles by 50 miles or something.
And I'll just to work off of what Jim was saying about green. It starts as green and then sort of decays off. When I go out for a night like this, often early in the night, it's just this green sheath at the bottom of the horizon, and then it's sort of, as it sort of intensifies, you get the other colors above.
There's more excitations going on over time. So.
When I was a child, I saw a yellow light. It permeated the entire forest that we were in. It was very yellow, so it just yellow factored into this when I make that.
I've seen yellow. Yeah,
And there's-
probably must have been a strong storm.
Yeah, I've seen that talked about, and that happens due to that teardrop shape on the backside. There's something unique about that teardrop where yellow will form. I don't remember the exact conditions, but it has to be an intense storm, I think. Okay, next slide. Cool. Okay, Josh, you're a magician. This is fabulous. What are those streaks? Were they in?
Those are meteors.
There's a meteors, that's what I thought, yeah. So guess what? We got purple, right? Yeah, and red, but that's purple. So this is around 350 nanometers, shorter wavelength than green. Okay,
Where was that taken?
This was Lake Elligo in Craftsbury, or I guess it's technically.
oh yeah, if you click it, Josh caught me on this, I had the wrong label. Click it once, we should come up with where it was. Maybe I'm wrong.
I'm clicking.
Okay, it's not there. Okay, Lake Elligo. Next slide. Okay, NASA website. This is equivalent to going to Google and typing in NOAA or, NOAA space weather, 3 words. You click that, it comes up with the space weather report, just like, Weather Channel or National Weather Service. You get all of this and more. It's unbelievable. Okay, it'd be fun for kids to play with, actually. That's the website. Okay, next slide. So let's take a closer look at the sun's activity via this. So I got these out of sequence, right? So we're going to NOAA and NASA website to study the aurora. Corona drives the solar wind. Yeah, great. Keep saying that, don't I? Okay, hold the phone for a second, don't click. So here's the Earth, the sun's over here, it's sending the solar wind this way. This is the equatorial plane of the Earth, so we're looking down from the North Pole. This is the, am I right there? Equatorial plane, this would be the polar plane, okay. I think I got that right. Noon, midnight, rodeo plane, equatorial plane. Maybe I got it wrong. Oh, here it is. This is dawn. This is north, south, dusk. Okay. This is dawn, north, midnight. Okay. This is contours in cross-section cut, but they're really 3-dimensional, of the Earth's magnetic field being hammered by the solar wind. So click, Josh. Okay, notice how the flow of the solar wind around the Earth is being protected by our, yeah, I goofed on that. Okay, so at any rate, you get the picture, waves of solar wind hitting the Earth's magnetic field, the Earth's magnetic field protecting us, and one of the things that tell you that it's working are the aurora in a big storm. Okay, when you go to that website, this is what comes up. Okay, don't click yet. This is a little bit shorter wavelength, 173. We see some corona here. This wasn't a particularly active day. We're going to see an animation of what happens for the prediction of the aurora. This is a satellite that's looking directly at the sun. It's called a coronagraph, right? So it's blocking the sun, but we're seeing emissions from the sun, okay? And I want you to pay attention to this one. So something's going to happen down here, which blew me away. I did this one yesterday just for kicks. And I said, I got to grab this one because I couldn't believe what I saw. Okay, click. Okay, sun's rotating. Watch over here. There's a corona. What's that? It was the moon.
Oh my God.
The moon was what, full or dark? You know, but to this thing, it was full. All right? I couldn't believe it. So this website tells you if there's visible corona. It gives you a prediction of what we would see for aurora, which wasn't much. But these pictures were taken, I think, based on data. This prediction was based on data from the previous day. This explosion here would show up as something in the next day. So maybe there's an aurora, big aurora, the day after this, which would have been today. So it also gives you things like X-ray flux, right? You don't want to get X-rays, right, as a function of time. This is, I know, unfortunately, this is not, I think this is protons. This is saying there's an injection of protons happening due to this. And over here, this is important. This is called the KP index. If you want to know when they're going to be aurora, this is called the KP index. Type in NOAA KP index, 3 words. This comes up, all right? When it's above 5 or 6 or 7, you will see aurora, okay? And it's by time, so it will predict when you can expect to see aurora. The time scale's down here, okay? That would be your daily fix to know when there's going to be aurora. So if you get 5 or 6, you're going to see something. If it's 7, you died and gone to heaven. So, okay, next slide.
Jim, I was going to say.
No, this is for planetary. It's for the, yeah, it's integrated overall azimuth, I guess. Okay.
The two biggest storms last year in May and October, I think, were both above 8.
Yes, they were incredible. I mean, I gave you the heads up rides, I think. So we all were out there, like, 2, 3 a.m. and it was unbelievable. Okay, next slide. So these lines don't show up very well, but this is a magnetic field, these magnetic field lines, okay. The electrons come out of the solar wind. They're the main component here. So they're charged. They're moving down along these magnetic lines, okay. And one of the reasons they're doing this, I didn't say much about this, but there's also an electric field in play here. So what happens is, you don't need to know the real details, except that these electrons are really spiraling around these magnetic field lines, okay? So they're doing little circles, okay? And as they circle, they're also giving off light. And I believe the radiation is at about, it's not in the visible, it's around microns radiation, right? So it'd be like chest x-rays, right? So you wouldn't be able to see it as an aurora. At any rate, the electrons are getting accelerated, spiraling down, and they hit the Earth, and there's an electric field down here that helps to generate not only the collisions of the electrons, but also the size of the field that makes those excitations in the atoms. And these are contours of what the aurora would look like, and it's on the dark side. Okay, next slide. Solar wind simulations. This was one of the big days, Josh, I think. Let's see if I got it right. Sun's on the left, Earth's on the right. Coding number is about 100 miles up. Solar wind velocity, blue, 400 to 500 kilometers a second. About not quite 2/10 of the speed of light, which is pretty fast. That was, normally it's much less than this, like 0.5%. If you get numbers like this in a big aurora, they'll be at 700 kilometers, 800 kilometers, right, a second. Normals are below 400. So next slide, click. Solar wind plasma density, 15 particles per centimeter cube. Okay, so that's atoms, or protons. Okay, it's counting protons. In a normal situation in the Earth's atmosphere, at the surface of the Earth, there's like 10 to the 22nd, 10 by 10 by 10, 22 times of oxygen atoms at the surface of the Earth per cubic meter, okay? There'd only be about 1,500 if you did the math to get a meter here. Okay, so this is pretty low density, but that's what you get from the sun. And that has all these effects we see. Next slide. Okay, this is really cool. I mean, this is the cat's pajamas. I mean, this is it. We're looking down, right, way above the Earth, looking down. Here's the sun, right? We're looking down on the sun, and we're looking down on the Earth, okay? And here are these numbers. Here's plasma density. Per centimeter we saw was 15 in one case. I'm not sure what stereo A is. Must be another camera in the opposite direction. I don't know. Radial velocity, that is the speed of the particles getting to Earth. Here, look, I got up to 700. And again, stereo A, whatever the hell that is, it's up there with it. Anyway, these are pretty big numbers. Okay, and this was September. Okay, click. That solar wind rotates in a spiral. Okay, it's emitted, right? And so the ones that were emitted first are out here, and the new ones are trying to catch up. It's a spiral. It's just like stirring batter, right? Thick batter in a bowl. And then the Earth, you could see the reaction of the Earth. I don't know if you click, will it go to the next slide? Okay, so at any rate, it's a spiral, okay? It's not a straight line wind. It's spiraling and emitting. It's like the rotation of the galaxy, kind of, same thing. Spiral arms. Okay, next slide. Here's an aurora forecast. This was in a week, 10 days ago or so. This was a weekday, but at any rate, you'll see the animation of what happens. Okay, so this is the dark side. It's now dark in the United States. The aurora is not even hitting the border with Canada. The Canadians are saying, we want it. Yeah. Didn't pay your tariffs. So, okay, so the one I started the talk off with was red, right? The entire circumference. But you can see this, go online, you can do this yourself. Next slide. There it is. I mean, I can't not show Josh's pictures. There's the Lowell Mountain, you said. And I don't know. This one doesn't have any. Whoops. That's all right. Go ahead. We got to get going here. Aurora color versus height. We're almost done. Okay. Click once. Okay. Excited oxygen at high altitudes. Above 150 miles, right, we're getting the reds. Up to 150, so lower altitudes, we get the greens from the oxygen. Okay, next slide, next click. Nitrogen gives us blues above 60 miles. Or is that more purple? I can't tell. It goes purplish, maybe. And then, so above 60 miles, purple, and below 60 miles, blue. That's nitrogen. It's right next door in the periodic table, 7 protons, 7 electrons. Okay, next slide. There's some purples, yeah. Look at those clouds, yeah, awesome, yeah. Next slide. Okay, the impacts of high-intensity solar wind activity. Next click. There's AE. This thing got hammered. I would get called in the middle of the night. I have a prop over there. Josh, can you reach around? We've got some demos if people are interested. We're probably all worn up by now. There's a long case, long black case. No, it's on the floor. Darn it. All right, I'll put it on the demo table later. Back then, this is 50 years ago, we didn't have any calculators, handheld calculators, right? Best thing you had was a kind of desktop calculating machine. I would get called in the middle of the night. AE got hit by the solar wind, it's tipped over. What are you going to do about it? I grabbed my slide rule. I used my slide rule to figure out how much thrust we had to apply to put the attitude back where it should be. Okay, and I won't go into that, but at any rate, that's the way we did it 50 years ago. No stinking calculators. Okay, next slide. Severe radio communication interference, commercial and military. GPS degradation, that should be a D. A. Marine navigation degradation. There's all sorts of things that happen when you get high intensity magnetic fields and electric fields, by the way. Electric fields are there. I didn't dwell on them too much. If you get a G8 storm, like Josh said we had, AC utility power can be knocked out. So locally, it's possible that people lost power due to that G8 in May. 160 years ago, the Carrington event, 1859, was probably the largest solar storm, at least recorded by Western civilization anyway. It knocked out telegraphy worldwide. The aurora were visible in the sky for 2 days. There are drawings of this in the sky for 2 days, and people thought it was, the end days. It was the end days, right? But the telegraphy was knocked out. And that was the means of communication, particularly for military. Satellite orbit and attitude control. So the satellites would get knocked around. Increased level of cosmic ray exposure on our surface. So you might get a chest X-ray without realizing it during a G8. Okay, next slide. Thanks for your attention. I've got some backup slides, but I think I'll forego that. We're probably low on time. I could show the electric field. Let's do that. Click a few times, Josh. Back up. That's a fusion. Get rid of it. Get rid of it. Get it. You don't want to know. E equals mc squared. Solar cycle, that's good to know, every 11 years. And this was this year, and we're right about there now. Okay, this is actually on that website. Pull it right off there. Okay, next slide. That's molecular oxygen. It doesn't partake in the aurora. There's a floating electron that just didn't know what to do. Okay, next slide. Here's the electric field. Click, Josh. Okay, so that's when those electrons are coming down, not only is it the magnetic collisions going on, but there's electric fields. Click once. Maybe that right there is the North Magnetic Pole. It's up in Canada. All right? That's why that bright yellow is showing up even on a weekday. So all this activity is happening with electric fields in addition to magnetic fields. Okay, I think this is it. We can call it quits. Yeah. Okay. I want to fire up, Josh, fire up that thing right there, the globe. Oh, well, we could do that. Yeah, all right. Okay, well, we're going to do it over here.
Oh, okay.
Okay. Just bear with me a second.
We need lights.
Okay. No lights. Yeah, let's see. Red to red. I need a light. Is that red? That's red. Yeah. See if I don't get shocked here. I'm getting it in there. Okay. Okay. Here, Josh, here, hold that in your hand. Palm, one palm. One palm. Okay, watch what happens here. This is a coil of wire, generate a magnetic field. Oh, is it not plugged in? Let me see the world there.
I think it's plugged in.
I don't think it's plugged in. I must not have it.
Oh, the power's off.
Oh,
I had to shut all the power off.
okay, we can do it.
Do you
Turn.
want me to turn it on? Do
I think we're done, yeah.
you want me to turn on the power?
Yeah, but
It
we'll,
might turn because all the outlets
okay,
are off.
okay.
Do you want me to turn it on?
For people who, yeah, let's turn off the projector and blah, blah, blah.
I think you can leave the projector
I don't need the projector, we're done,
on, just
yeah,
not your,
yeah. If you throw the power off, we could do, so if there are any questions,
Yeah, Jim,
yeah.
I just wanted to, you didn't touch on this, but in 1975 and 1977, two spaceships, probes, left Earth, Voyager 1 and
Oh,
Voyager 2.
yeah, that's right.
And just recently, they have entered the wind of interstellar space.
Right,
And
that's
I
right.
believe the extent of the solar wind goes to the heliopause, or is it the heliosphere that designates?
I think it's the magnetopause, because they're kind of different things, I don't know.
Anyway,
But you're right, they're way out there.
This wind that you've been talking
Yeah.
about goes all the way
Oh, yeah, yeah,
out to the edge of
That's
solar-
right.
the sun's influence in the universe.
that's right.
Which is, and now these two spacecraft have gone further than anything
Viking,
from Earth,
Yeah.
Lightning.
Viking, they were called the Viking spacecraft, Viking.
Voyager.
Oh, Voyager, that's right,
Voyager
Voyager,
1 and 2,
right,
yeah.
that's right,
So,
yeah. Yeah,
I have two questions, one easy and one not so much. What's the period of the sun? What's a day of the sun and its rotation?
oh, I think it's, I don't want to misspeak, but it's, based on what you see, that's like 15 minutes of data, it's probably, if that, it's probably a couple days, I don't know. I could be entirely wrong.
Right.
Yeah, it's a big, big thing rotating, yeah.
So my other
It's probably
question-
many more days, I'm gonna guess.
So we talk about electrons and their shell, but you can't measure the position, you can't measure the speed. And I'm like, 50 years ago, chemistry, electron jumping, we have this idea that there's like a sphere and they go travel around that sphere or something.
Mm.
Can you describe more what's actually happening there?
First of all, it's all 3D. These orbitals and so on, basically exist in 3D. Even the dog bone ones, take a dog bone and rotate it in 3D. It's literally a dog bone. So my interpretation would be those electrons that are in the dog bone or the spherical, they're anywhere on that spherical shell, anytime. I mean, you just don't know where it is on the shell. And even if you could measure, Ray talked about this, even if you could identify its position on the shell, you wouldn't know how fast it's going, so you don't have all the information. You just can't do it. It's a quantum conundrum.
yeah.
You can know one, perhaps, but not know the other. So I'll just end by saying, I think to me, like the hydrogen atom, it's like that if you took that orbit and kind of, from the center and spread your fingers, there's a distribution of where the electron can be in that dimension. And if you rotate that around, it looks kind of like a fuzzball, right?
So the orbits, they're not discrete, they're variable energy levels?
No, the energies are absolutely discrete, absolutely. It's been measured, those orbitals been measured to like the 10th decimal place. It's unequivocal, absolutely unequivocal. The energies, you can know them really well, but you just don't know where the electrons are. Yep, you just can't, yeah.
Thank you.
Yeah, great question. Yes?
Are the Earth's magnetic poles of equal strength, north and south?
That's a good question. I would say they're roughly equal. The Earth is not a perfect sphere. It's large at the equator, right, and flatter at the poles, and the interior has lumps in it too. So that core, I think part of what we're seeing with the core thing, where there's seems to be 3 rotating solenoids, it's probably because the mass distribution isn't exactly.
So if Josh went to Tierra del Fuego,
Uh,
would you be able to take pictures of?
Oh, I'm sure.
Borealis?
Oh yeah, oh yeah, oh yeah, yeah,
The southern is
yeah.
Aurora,
Yeah.
Yeah, you go to this website, they give both north and south. They don't, what's it called?
You also mentioned, earlier in your presentation, you compared the Earth to Mars.
Uh-huh.
And Mars has a solid core, and therefore
That's the thought.
The strength is
Yeah,
different.
that's,
What about Mercury and Venus? Do we know about that?
well, let me just elaborate on the Mars. It's pretty clear Mars probably had an atmosphere, probably had life, probably had water, and probably had a rotating iron core. Mars is like just about half as big as Earth. We're a big planet. All the heat is contained in there. It's not leaking out. I think the heat leaked out of Mars. The iron core solidified. There's probably a remnant core there. Minute magnetic field, but nothing like we've got, a very active magnetic field. And then because of the protective effect of the magnetic shield, things on Mars just, what life there existed died, right? And there was nothing to sustain an atmosphere, right? So the atmosphere, there is a slight atmosphere. It's not much. I don't know a whole lot about it, but it's a tad. Yeah. And then Mercury. Mercury's just too damn close to the sun. It's really hot. And I think one side faces the sun all the time, so it's really hot on one side, and it's really cold on the other. Venus, I think, people probably know better than me, but Venus was a active planet, but then it had, what do we call the runaway, the environmental? We got runaway temperatures, right? It got too hot. It's 1,100 degrees Fahrenheit. It's too hot to live in. So, yeah.
Do they know when the poles are going to flip again?
Oh, great question. Great
And
question.
what it's going to do?
Great question. Beautiful question. Right now, for at least 100 years, they've been counting sunspots, and I showed a piece of the graph. It seems to be fixed on 11 years, right? So the best knowledge that I've seen is that every 10,000 to maybe 100,000 years, the sun's magnetic poles flip. And the reason is, I got a demo here. I got a top I bought at a kid's store, Woodbury Mountain. By the way, all this stuff here I got at Kohl's because I couldn't find anywhere else, so Kohl's came through. But you take a top and spin it, right, the old top. As it slows down, it'll flip. Okay, so as the internal structure of the object is changing for whatever reason, it will flip. And it may speed up because now the Earth's getting heated more over here than there. And it appears to be every 10,000 to 100,000 years, somewhere in there. And they've taken data at the bottom of the seafloor, and they can actually see stripes of magnetized lava. And you had another question, am I right?
Do we know when it may happen again?
I don't think it's predictable. I don't think it's
Does it
predictable.
flip quickly or take like?
Yeah, I think I don't think it's quick. I think it's going to be integrated over time, 1,000 years or something. But during that time, there'll be a few days or maybe a few months where we're feeling bad stuff from outer space, right? Because the field is now lower. By the way, in that Carrington event, they figured that the atmosphere, the physical atmosphere, was pushed down to 60 miles. The normal atmosphere, the measurements are taken, the satellite I worked on was 90 miles but the atmosphere, they figure, is about 300 miles at max, right? on average 150. During that Carrington event, they figured that the Earth's physical atmosphere, all the gases were pushed down to 60 miles. The solar event?
But just on one side,
No, it was days.
no, one side of the Earth?
No, it was rotating. Yeah, it was worldwide. Worldwide.
Yeah, the other thing about the Carrington event is that it was visible from the equator. Like, it was just completely the whole planet. Yeah.
24/7.
When was this?
1859?
Yeah, 1859. And in addition to the telegraphs going out, for a minute, the charge from the Aurora was powering telegraphs.
That's right.
So the telegraph operators were like, I think I'm out. Are you out? But we're talking. I guess we're not out. Like, I
Dave,
guess this is still working.
Dave, don't turn me off, Dave.
Yeah.
What does it do to the human body?
Sorry?
What does it do to the human body,
What's that?
the solar wind event?
It protects us. We get point, I looked this stuff up because I wanted to know. I wanted to know if Musk was going to live, going to Mars. He's going to die. He's going to die. All right, so normal radiation levels are about 0.05 millisieverts, just for a number, right? I went in and had an X-ray a couple weeks ago. I got 6 millisieverts, not 0.5, but 6. That's a chest X-ray. So you don't want to be getting, and then you get the more, big, full tomography scans. You're getting, 20 or 30.
Wow.
All right, something like that. Don't quote me on that, but a chest X-ray a year is okay, but massive chest X-ray, full body, 10, 15 millisieverts for 300 days to get to Mars and how long to stay there, you're gonna die. You're gonna die. It integrates out to like 3,000 millisieverts. In other words, 3 sieverts, and that's a big number. Yeah.
Were you asking what happens to our bodies
Like
just in a normal
Oh.
storm, if
Yeah,
anything
like
happens
when
to
it
us
comes-
on the Earth?
When
Yeah.
it hits Earth, what
Yeah.
is it doing to us?
It's protecting us. By and large,
Our magnetosphere is protecting us.
if we didn't have magnetic field,
Yeah.
we'd be Mars. We'd be Mars. Yeah. It's forcing most of the electrons and protons and actually cosmic rays from the rest of the galaxy and outer space. Most of that stuff, I don't know this in all detail, but it gets pushed around, right? It's literally throwing a block like a football player for a running back, right? Yeah.
What causes the magnetic poles to move?
Just the, I'm going to guess, just the non-uniformity of the iron core. It changes its.
I've heard the North Pole is moving quite a lot.
Oh, it is, yeah. That arrow points. It actually used to be, I don't know, 500 miles north of there 20 years ago.
Right.
It moves quite a bit, yeah. So your compasses, if you get, north of that arrow, you're going to be pointing south. Yeah.
Jim, I have 2 questions.
Yes.
How many X-rays would you get going through the Van Allen belt?
Oh, okay, so the Van Allen belt.
Oh, yeah.
All right, so there's the ionosphere, and the ionosphere is basically the charges in the atmosphere that are created by the solar wind, right? And that's up to 300 miles. The space station is what, 250? Something like that? Circular orbit, and they have to fire the thrusters so it doesn't decay. So they worry about what the astronauts are getting, right? So they're probably getting the equivalent of a full body X-ray every week or so, right? Not insignificant. And there is data out there on that. I could have spent a lifetime studying stuff, but it's, yeah. Suffice it to say, the astronauts are getting much more radiation than we are. To be a concern, yeah.
You made a statement, you said that in the middle of our galaxy, there's a
Black hole.
black hole.
Yeah.
2 questions. How large is it and how intense is it? And what effect is it having on all the planets and stars and
Well, I can say I don't know a whole lot about this, but so a black hole is a region in space-time where nothing can come out, and it has a definition of a radius, right? And the radius of the Schwarzschild radius in, I think, our black hole, which is the equivalent of, I'm going deep in memory, maybe 100,000 suns of mass as we know it got sunk into that black hole. So it has a width, let's call it. The galaxy is 100,000 light years, and I would say the black hole's, not even a light year. It's pretty small. But it's significant enough that the one problem, this I know a little bit about, one problem with models of our galaxy is that they found that as you move away from the center of the galaxy and you encompass more stars, the speed of the rotation should pick up. But once you got farther out, the speed of rotation of the galaxy was supposed to die off. They had many measurements, and a woman, Vera Rubin, I grew up in DC, Carnegie Mellon Earth Institute was in Northwest, right next to where the vice president is on the Naval Observatory. She figured out with astronomical data that the galaxy rotation was uniform as far as you could see, you could tell. That's dark matter. That's matter that is not the black hole, but it's something that has mass that we can't detect. That explains why the galaxy rotates at the same velocity, just like half a billion years, something like that. And the other part of your question was?
Well, it's the center of the universe. A universe, what power does it have over the whole contractile?
Oh, okay. Well, this was the galaxy, all right? The galaxy is one of a gazillion galaxies in the universe, right? So something was discovered recently. I don't know if it was the Vera Rubin telescope or the Webb telescope. So the thought has been for like past 30 years that the Big Bang happened 13.5 billion years ago, okay? And for 300,000 of those years, if you ever watched The Big Bang Theory, it's a hot, dense state, and that was the universe up to 3,000 years. And then, what was it called? The expansion was going on, but there was a flip where actual matter as we know it formed about 300,000 years ago. So all the galaxies in the universe that have been detected go back to about 300,000 years. Before that, they surmised that, okay, the Big Bang had to occur. And there was a famous measurement made in 1960 that detected a background radiation of 2.7 degrees Kelvin, 2.7 degrees above absolute zero, minus 473 degrees Fahrenheit. They found this trying to tune up the antennas that are used right now for your wireless, right? The wireless towers. They were developing the first radiation horns at AT&T, and they couldn't get rid of this noise. What the hell's this noise? Oh, they wrote a paper that said, well, we cleaned off even the white excrement. They thought pigeon poop, and they couldn't get rid of it. Turns out, at Princeton down the road, the professors were trying to figure out exactly what they detected. And they were scooped. So those engineers got a Nobel Prize in physics, and the eggheads at Princeton got nothing. So the new either Vera Rubin or Webb discovered a galaxy well into the first 300 years. Something's not right. Something's not right.
But they
with it.
also found out, they think almost every galaxy has a black hole and that.
Oh, yes.
Absolutely
The-
essential.
Absolutely true. For the large galaxies, you have to. For the certainly the spiral galaxies, you have to. And in terms of what happens, things continue to fall until it gets a little bigger, so it will affect the evolution of our galaxy, the one we have, which is 64,000 suns or whatever it is. Yeah.
So the perimeter of a spiral galaxy is traveling at the same speed as the interior? You would expect it to be faster.
The rotation on the inner, say, third, let's call it. So 100,000, the first 20,000 light years in the galaxy, the speed of rotation is picking up. At that point, you've got most of the mass in the galaxy, and you get out toward us, we're in a kind of a sparse. And then the rotation, you just do the math, the rotation's got to fall off. It's Newtonian physics, okay? So they have discovered that no, we're rotating at this same rotation rate that something's about 20,000 miles from the center of the galaxy. We should be well below that rotation.
Okay, but if we have, like, the rotation of an object around the sun,
Uh-huh.
it has to be faster at the perimeter in order to stay integrated. Is that not right?
Well, the scale is so much different. I don't know how to answer your question. For the galaxy, for the solar system, Newtonian mechanics, it goes back 300 years, right? Works perfectly. When I worked at NASA, they were using straight up Newtonian physics. No Einstein, none of that, right? And they're successfully launching satellites. It explained all the periods of rotation of all the planets we know about. But the scale of the universe is different. It's also, why we have a spiral galaxy in some cases and not in others. I think it has a lot to do with black holes, but what was your question? Why aren't we rotating?
In my mind, I think of something that's staying attached to a center core has to go faster.
Well,
at the perimeter.
you saw that it's not the case with a solar wind. It's a spiral.
Yeah.
It's a spiral. Yeah. The lateral rotation velocity is about the same, but it's the speed of it's a balance between the outward flow and the lateral flow associated with that. So it's a spiral. It's a spiral. I think it's analogous to what the spiral galaxies do.
Is that related to like electricity traveling around a wire that goes in a spiral? Is that a different phenomenon?
I think the electricity around a wire is what defines a magnetic field. I don't know in terms of gravity, right? Remember, gravity is operating on this huge scale, and it's an entirely different force. It's a force in 4 dimensions. Electricity and magnetism operate in 3, to the best of our knowledge. It's that 4th dimension, time, that screws things up. Yeah, where space and time get mixed.
Distorted, twisted.
Yeah.
Well, thank you.
Yeah.
So,
Okay.
so
Yeah. Do we have power?
You have power.
Okay.